All right, hitting the high points from yesterday. Remember, these are your 6 strong acids. Just throwing it at you. When you hear the word strong, what does that mean? 100% dissociation. Okay, if it's not a strong acid, then it is automatically a weak. Okay, so you don't have to memorize any weaks. You need to recognize them just to make sure. There's be a few that you recognize, but these are your 6. We said sulfuric, nitric, perchloric, hydrobromic, hydrochloric, and hydroiodic. 2 things I want to go back and hit real quick. Perchloric, HClO4. If you do your own research, if you look in a book, if you try to look up a list, you may come across chloric acid, HClO3, listed under the strong category. That is still up for debate among the chemistry community. College Board, as of today, does not recognize it as strong. So if we ever do anything with strong acids or weak acids, you're probably not going to see chloric acid as one of the options to work with because of that dispute. But I just wanted you to forewarn you in case for some reason you come across it in any of your research. Just know that College Board does not accept it. And don't ask me why. I'm not getting into that. Okay, but that is one of the things. The second thing is, notice what halogen is not a strong acid. Hydrofluoric acid. You good? Okay. Thank you. I'm glad I don't really want to talk about it. We talked about oxyacids. These are your polyatomic acids. That hydrogen is broken off by hydration forces. Then we talked about weak. Remember, they dissociate less than 5% of the time. And we talked about the carboxyl group. We talked about carboxylic acids, and these are some other sources of them. And I know the 2 that are the weirdest to you guys are amino acids and nucleic acids. You don't associate them as an acid because they're the building blocks of your proteins and the building blocks of your DNA and RNA, right? You've never really heard the word acid as an acid. You just said, "Oh, that's an amino acid," but you didn't really realize what it was. And that has to do with the ability of the hydrogen to break off and make a change in pH. Okay? All right. Now, then we talked about some things that don't, and then we talked about, this is where we stopped yesterday. So, other covalent compounds that ionize in solution. Compounds that contain the hydroxide ion. Now, I'm going to go ahead and tell you right now that this right here is a big, huge, bold, fat lie. It does not have to have a hydroxide to be a base, and we're going to talk about that in just a minute. Okay. Now, there are, and you do not have to write these down. I don't know where I'm going with all this. Okay, there are 3 definitions of acids and bases. Again, you don't have to write this down. One, this was, and I always misspell this guy's name. Okay, Arrhenius. And then the second group was Bronsted-Lowry. Okay, and then the third guy was Lewis. We will talk more about this later. We'll talk about what each group or what person said. And here's what and this is just kind of the basics. Arrhenius said that acids equal H plus and bases equal OH minus in solution. This was a really, really, really long time ago. What we learned over the years that he was wrong. Okay, but we still use his basic assumption as to be partly true, but we had to adjust for it. Okay, Bronsted-Lowry said that an acid is a H plus donor, where a base is an H plus acceptor. Now let's pause and let's think about this. Does that logically make sense? It does, okay? All acids, do they have an H that they break off? And they throw it into whatever. And the base is there to accept it. Okay, and we'll get more in depth of how that works later on. And then what Lewis said, and this is where it gets really weird, and as a matter of fact, I'm only showing you this to deepen your knowledge. Lewis acids and bases are no longer tested on the AP exam. Now, personally, I think that's a mistake. I really wish they had left them on there, but they are no longer specifically asked about. He said that acids are electron pair acceptors. And I know what you're thinking, what in the world is he talking about? And he said that bases, just go ahead and open it. Okay, just making sure. Electron pair donors. Okay, And I'm going to show you how that this is true in just a minute. This is the most complete definition of what an acid and base is, but we have 3 of them to go off of. So oldest, not old, and then newest, if that makes sense. And again, I don't know what years all of these things were delineated out, but it is the truth. And we'll talk about how we come up to this. Does that make sense? We go with that? Okay. All right. So this is why I said this is a lie. Do you have to have a hydroxide for it to technically be a base? No, but here's all the best news. Remember we talked about there's strong and weak bases, right? All of the strongs have a hydroxide. Okay, that's the best news. Just because it doesn't have one doesn't mean it can't be a weak base. So when these compounds are dissolved in the water, the cations and the hydroxide ions are separated. Now, so what I mean by that is that if you have XOH or YOH2. Now my first question is, what is the difference between X and Y? They are different elements. Huh? Very good. Okay, so let's just hypothetically say that this is a group 1, and let's hypothetically say that this is a group 2. Okay. How about Q? Is that better for you? Okay, Q makes sense. All right, so Q is a group 2 where X is a group 1. So when these things dissociate, you get X plus OH minus, and here you get Q 2 plus OH minus. Now, this is something that we're going to have to adjust to. What's wrong? I don't care. Get over it. If I did this and I said, yep, I'm done, I'm final, I'm circling this and moving on, would you have earned credit? Why not? Now, my first question is, you see this as the issue. I do not see that as the issue. This is where I need to start training your brain to look at it from 2 perspectives. My first question is, what is the charge of both of these compounds on the left? Okay. They are both neutral. Stop. Up here, I have 1 positive and 1 negative. So what's the overall charge? Neutral. So do your charges balance up top? Up top, yes. But what is your charge on the bottom one down here? This is neutral, but what is your charge differential? You've got 2 positive and you've got 1 negative. So the difference is, or the net charge is 1 positive. Is that a problem? Yes. So this is the new transition that we're going to start looking at. Not only do we have to make sure our atoms balance, we also have to make sure our charges balance as well, right? So how can I fix this from a charge standpoint? Just put a 2 in front of. Now, that makes logical sense. You could have done it the other way, but we're looking at it from a different perspective, okay? So this is kind of what's going on. And this would be, if you took a litmus paper and you stuck it down in there, or a pH reader and stuck it down in there, about what range would your pH be in? Above 7. Okay, it would have to be above 7 because there is a hydroxide in there. But whose definition would that be true according to? Arrhenius. Okay, this is Arrhenius' definition. Now, these compounds that do this are called bases. Now, strong bases, such as when solid NaOH is completely ionized in solution. Other example of strong bases are this. These must be memorized. So now that we've seen this, I actually wanted to do it today, but we ran out of time. We didn't get a chance to do it. Tomorrow, you have a quiz on the 6 strong acids and 8 strong bases. You need to know them backwards and forwards. It is 14 things. Get over it. You're going to spend more than 14 minutes on social media between now and the time you go to sleep. You can spend 14 minutes in memorizing 14 things. That's how I'm doing it this time. Yes, you need to spell it the whole way correctly. Now, obviously, you don't have to write hydrochloric acid. You can just write hydrochloric. And right here, you need to be able to write both of these. Okay? So, now, why did I put that line there? Above the line is group 1. Below the line is group 2. Now, there are 2 exceptions. Now, What is the exception we left off of group 1? Francium. Just like astatine, we never talk about francium, right? He's the old decrepit man that no one ever really likes to talk about. He is very grumpy. Okay? That's why I said decrepit and grumpy. Yes, very good. This is Q, but these are real Qs. Nothing. Now, the two that we left out of group 2 are beryllium and magnesium. Now, there are other reasons than the fact of that they are too small, but there's also that thing called too much Zeth, and we're not going to worry about any of that stuff, okay? What's wrong, Justin? I know they're in the wrong order. Stay with me. And radium. The bottom rows we never talk about, okay? Now, the one thing that I want to point out to you is that, yes, the group 2 elements are written out of order on my list. There's a reason that they're written out of order. And it's a mnemonic device that I tried to teach you guys, and I have 2 of them, and I don't care which one you pick, okay? They both begin the same way. The first one is it's group 1 and CBS of group 2, or it's group 1 and Cabasur of group 2. Calcium, barium, strontium, Cabasur. Group 1 and CBS, or group 1 and Cabasur. They mean the same thing. You're just using the second letter. The reason I like CBS is because I watch CBS all the time, so I can remember that. CB is in boy. Okay, so what do I mean? It's CBS or Cabasur. And the reason that some students choose to use the Cabasur is because in group 2, is there another B? It's beryllium. So that's why they like the Ba part versus just the CBS. Sir? Yeah. We use periodic table on everything. I mean, it's not cheating. It's not cheating. Remember when we first had this class last year that I told you I'm going to teach you how to cheat using the periodic table. It's if you cheat on every single chemistry test if you know how to use a periodic table. I'm dead serious. Like, I want you to think of it that way. Yes, ma'am. You good? Strong acid, strong basis. Yep. Formula and compound. Yes. Yes, ma'am. They're all going to be 100% soluble or 100% ionized, and we'll talk about that on the back end of this chapter. Yes, ma'am. Yes, ma'am. Okay. Now, weak bases. So, if it's not one of those 8 that we just looked at, what is it automatically? Weak. You don't even have to think about it. If it's not one of the strongs, it's automatically a weak. The one weak that I need you to have memorized is this one. Okay. NH3. Ammonia is a base. Okay. That is the only one that I absolutely have to have you to know. Okay. Now, what do you notice is the difference between this compound and the other strong ones? It does not have the hydroxide ion. So, whose definition did this destroy? Arrhenius. Okay? So, here's where we can actually talk about the other 2 guys. And I want to show you this so you understand how and why. So, according to Bronsted-Lowry says acids are hydrogen donors and bases are hydrogen acceptors. We cool with that? So, watch this magic. Okay? So, do you agree that I have NH3 and this is a base, right? And according to Bronsted-Lowry, they said that bases are what? Hydrogen acceptors. So I've got a hydrogen ion. And what does the hydrogen ion what does it represent? An acid. Okay. So here's what happens. You guys are smart enough to know what happens. Good. Okay, so this is what happens. So, My question to you is, what happened? It's synthesized. I like that. It's synthesized. So the ammonia accepted the hydrogen ion. True. This is what happens. That's Bronsted-Lowry. Okay. Question. Go ahead. Yes. Yep. Okay. Now, let me show you Lewis. Lewis, now have you ever heard of Lewis before? What did he have to do with? Lewis structures. What do we always have to count? What are dots? Amazing. Lewis talked about electrons. So let me show you the Lewis structure version of what happens here. And according to Lewis, Lewis said that acids are electron pair what? Acceptors, and bases are electron pair. Watch this magic part too. True or false? If you had me last year, do not answer this question. This is for Crocker only. Name that shape. Shh. We go with that? Stop. Trigonal pyramidal. Yes or no? Yes. Trigonal pyramidal. Polar or non-polar? If you've had me, don't say a word. Definitely polar, okay? Because here's the deal. The pair of electrons is pulling up on this thing, right? And those hydrogens are all pulling it in opposite directions. Which end wins? None of them. No end, well, excuse me, the electrons in. Nitrogen wins, so it's going to be pulling it up to the top, right? So it's a polar molecule. All right, next question. Bond angle. What'd you say he can answer? What did you say? What'd you say? You said 107? You're actually right. 107. Okay, this is 107 degrees. Here's the fun one. Don't say it out loud. Let everyone think before someone says it. Hybridization. How many S's are there? Okay. How many P's are there? Very good. Are there any D's? sp3. So trigonal pyramidal, sp3, 107 degrees, polar, anything else? Oh, which, don't say it out loud, which intermolecular force would this exhibit? We just talked about this yesterday. Okay. First of all, we said this is polar. Okay. Polar only goes with dipole-dipole and hydrogen bonding. At a minimum, hydrogen bonding has to have what? At a minimum, a hydrogen. If it doesn't have a hydrogen, it's impossible. Okay. Does it have the other part? Yes. So this is a hydrogen bond molecule. Okay. Now, so here's the deal. You've already told me that this thing is a base. So let's get back to business. According to Lewis, bases are electron what? Donors. Electron pair donors. So let's come back and let's look at this thing. Does it have an electron pair to donate? It sure does. Now this is amazing. Let's continue to watch the magic happen. Now, according to Lewis, if bases are electron pair donors, then acids are electron pair acceptors. According to this H, it is an acid, right? How many electrons does that H positive have? None. Why does it have 0? It's positive. It's gotten rid of it. So remember, what is the minimum number of electrons that hydrogen needs to become noble? It needs 2. And who would it look like? Helium. Well, who has 2 that it could be willing to donate it? Nitrogen. Amazing. So when we have this, we all of a sudden magically get this formed. You with me? So, does the logic make sense now? We've seen it both ways. We've seen the Bronsted-Lowry, because the base is a hydrogen acceptor and the acid is a hydrogen donor. But Lewis says that bases are electron pair donors, where acids are electron pair acceptors. Is that exactly what happened? Yes, you've seen them now both visually. Now, Mason's already ruined the fun of this. What is the shape of this thing? Tetrahedral. Anybody know the bond angle? 109.5. Polar or non-polar? Nonpolar, that automatically means the LDF is? The IMF is LDF, and hybridization, how many S's? 1. How many P's? How many D's? None. Okay? Shh, shh, shh. I don't know what you're talking about. Okay, remember the hybridization, you put a flower petal around everything touching the central molecule. So, if we went, yes, so there's 1, 2, 3, 4. So the exact same. Now, technically, truthfully, do you see how I drew this and how I drew that? Really, this is more like this. And this is I think something that you guys need to see. As far as the hybridization goes, does it look very similar in shape? It does. But here's what we talked about a long time ago. Remember that we said that electron pairs take up more space than a bonded atom. Now, look at your bond angles on both of these. The ammonia, which is a trigonal pyramidal, is 107. Look at your tetrahedral. What's the bond angle? 109.5. So which one has a smaller bond angle? The ammonia, the trigonal pyramidal. So what caused the change in the bond angle based on the structure? The electron pair. Visually, now does it make sense? Yes, sir. Okay. It is. It's actually both. It is amphoteric, and we'll talk about that. Stop. We'll talk about it later, Mason. That's a very good observation, though. Okay. Now, so up here, do you agree that the nitrogen is more electronegative than the hydrogen? Okay. So here's what's going to happen. Do you remember how we said it points like this? Do you agree that all 3 of these are going to be pointing in this way? All right, so because of that, all the electrons are going to be flowing to this region. So this region is going to become partially negative. Now, in fact, it's actually going to become 3 partial negatives. Why? Because it's pulling in 3 electrons. Over here, which hydrogen is going to be pulled the least strength? It's all pulling in the same direction, right? So it's all going to be centrally located right there. So there's no way to disperse. They are evenly spaced. Say it again. This. So how do I turn this into the ammonium? Excuse me. This is the ammonium, right? How do I take this and turn it to the ammonia? Take off the top one. Now, when I take the top one off, I replace it with a pair of electrons, right? Do the pair of electrons take up more space or less space? More. So it's going to take these and bend them down. That's why your space between them is different. Does that make sense? Yes, ma'am. 3 max. Yes, you can have theoretically up to 5Ds, but experimentally you can only ever get to 2. Because the largest molecule we ever have is octahedral, and it's sp3d2. That's as big as it gets. Yes, sir. That's a good question. It's something you have to memorize, and the way they do it is wherever the smallest bond angle is between atoms, not electron pairs, atoms. And again, it's something you just have to take a list and memorize them all. And I hate to be that way, but there really is no way to teach that. Nah, I don't think any one of those are on there, no, but that's something you do need to start looking at. Okay, so the composition of solutions. Now, what is a solution? Okay, it's a mixture of 2 different things. Okay, is there such thing as a solid solution? What do we call those things? Alloys. Okay, I guess I should have said a metal solution, an alloy. Okay, so if we have something that is in the liquidy state of matter, we don't call it a liquid, we call it a what? Aqueous solution. Okay, the aqueous solution is kind of like the Department of Redundancy department. They mean the exact same thing. Okay, aqueous means solution, and solution means aqueous. But aqueous tells you that water is present. You got it now? Okay. So chemical reactions often take place when two solutions are mixed. To perform stoichiometric calculations in such cases, two things must be known. Number one, the nature of the reaction, which depends upon the exact substance and whether or not the substance exists as ions or molecules in solution. So really, we need to know if what we're mixing is soluble or insoluble. Okay. Number two, you need to know the amount. Well, to do any stoichiometry, do you have to have a gram, a mole, or a volume? Yes, you've got to have one of those things. Can they give you a pressure and a temperature and a volume and you get moles out of it? Yes, that's Pivner. Okay, we can work with all those things. So probably going to have to convert to moles normally. They either give you grams or they give you concentration and molarity, and then you got to get to moles from that. But that's really kind of what's going to be going on in this particular section. So molarity, how important is this? It is the bane of your existence because it will be here forever. It's actually more important than stoichiometry because if you can't calculate, if you can't use molarity, you can't even do the stoichiometry. Okay, this is the beginning step. First of all, you got to balance an equation. Take that back. You got to be able to write an equation. Then you got to balance it. Well, then you're in for a long road. Okay, so we've got to be able to do all those things before we can even get to the stoichiometry part. Because if you don't know what your formula is, you dang sure ain't going to know how to convert the number of moles, and then you're dang sure not going to be able to find the limiting reactant. So all of those things are. What's wrong? Dang sure's. Okay. All right. So we know that molarity is mole per liter. Problem number one. What if they give it to you in grams? Convert it to moles. Problem number two. What if they give it to you in milliliters? Convert it to liters. Is there such thing as millimoles? Yes, but I'll kick you in your teeth if I see you write it on the test. Okay, so do not ever write that. So, may have to add volumes if things are mixed. Keep that in the back of your skull because we'll talk about that. Let me give you an example. You have solution A and solution B. I take solution A and I pour them in solution B and I pour them into a bigger container. Number one, do I have a certain number of moles in A with a certain volume? Do I have a certain number of moles in B with a certain volume? When I pour them together, are the moles additive? Potentially. We'll talk about how and why. Number two, are the volumes additive? Yes, keep that in mind. Okay, only when solutions are mixed. All right. It can be written in two ways. Now, this is something that's new to you guys. It's going to be imperative that you're going to be able to use the rest of the year. If you see a formula written in brackets, are brackets different than parentheses? Yes. If you see a bracket, it stands for molarity. Yes, it is important. Yes, it is aggravating. But yes, you must comply to the rules. When you see a bracket, it represents molarity. Yes, ma'am. Like the one right there in yellow. You do not have to write the M. You can put it in brackets. Yes, sir. I kind of like it personally. I'm sorry. Okay. So, if you want to know the molarity, you can do 0.75 moles divided by 1 liter. Now, what is 0.75 divided by 1? 0.75. That's going to be your concentration. Now, is it always going to be that easy? No, the volume of 1 is very rarely used, and I wish it were used more often, but that makes it too simple. So again, brackets represent molarity. Now, my next part, and if you want to write it above this or below it, wherever you want to write it, some of you love this thing, some of you despise it, but I don't really care. Okay? So, here is what we have. Molarity is moles divided by liters. You should never, ever mess up a molarity rearrangement. I would hope not to. Just like you would expect people never to mess up density either. Would you like to see density? It is Department of Motor Vehicles. I think I told her that. So that is density. Density is mass divided by volume. So you should never, ever, ever mess this up. Okay? It is Almost. Okay. All right. So preparing solutions. Now, hint. Huh? Q equals MCP delta T. This is the specific heat formula. It's really not bad, sir. I have no clue what you're talking about. Okay. Now, hint, hint, wink, wink. I draw a big circle around this slide right here. I'm telling you now, you're going to have to do this on the test. My test. Okay. I'm telling you now, this is going to be your best friend. And here's what this is. This is using your words of how to prepare a solution. So if I said I wanted you to go make me a certain concentration sweet tea, let's just make it simple. Instead of making it something like silver nitrate, let's make it nice and easy. Let's make it sweet tea. At a minimum, and we're making this in the chemistry lab, not at home. Okay? What would be some glassware you may want to use? A beaker, maybe graduated cylinder. Think about what you need to make sweet tea, but let's a weigh boat. Okay, something, a stirring rod. Let's not go with the Bunsen burner. Let's go with a hot plate. Okay. What are some tools? What are some more tools? All right, a magnetic stir. That's fine. What about something to weigh the sugar? A digital balance. Okay. All right, so we've got a digital balance and a weigh boat to weigh the sugar. Okay. We've got a beaker to pour the water in, right? We've got a magnetic and a hot plate to heat it up and to stir. And a stirring rod to stir once we do it. Sure, if we want some gloves, goggles, obviously. Okay. Anything else? That's supplies. We're talking about equipment. Okay. Now supplies are the given: water, sugar, and tea bags. Those are givens. That's your supplies. Too bad. We're in the South. We drink sweet tea here. If you don't like sweet tea, move north. We're in Dothan, Alabama. Okay. Too bad. Now we may not want to use Dothan because people could say, well, you're making meth too. But no, we're making sweet tea. All right. So here's the deal. You could walk me through exactly how to make it verbatim, step by step by step. But we need to make sure that the way we say it, the way we write it, is proper chemical language. Okay? We're talking about the right equipment, we're talking about the right supplies, and we're talking about the right way to perform that action. Okay? So, who can I pick on? Nicole, since you don't like sweet tea, I'm going to pick on you. Nicole, just very basic, very simply explain to me how you would make sweet tea with the chemical tools we've already discussed. All right? No, the sugar is separate from the tea bag. Let's say 1 liter of sweet tea. Yes, ma'am. All right, we'll say 1 liter and we'll say 15 grams of sugar. You tell me. I'm not helping you out any more than that. Tell me what you would do. Perfect. Okay, I like that scale thing. Yep, that's great. Okay, continue. All right, good. Yes, perfect. I like it. Very good. Okay, good, great. No, they're already in bags. We'll say 3 bags. Yes, ma'am. Just a hot plate. Yep. Okay. Very good. So could you use a thermometer? Sure. I like it. 100 degrees Celsius. Okay. Oh, slow down. All right. This is a question for everybody. Does anyone know what it's called when the water goes into the tea bags and pulls the tea out? Say it again. Very good, Steve. Okay. Who are you? What is herbal tea? Come on. Uh, you disappoint me greatly. Let me guess. You are in like pumpkin spice mode, aren't you? Okay. Then let's continue this. I don't drink it a whole lot either, but it's something easy. Okay. No, let's put it in the beaker. Let's leave it in the beaker. This is a chemistry lab. Let's leave it in the beaker. I understand, but we're not drinking this sweet tea. We're just preparing it. We're preparing a solution. Okay. Okay. Will it dissolve all on its own? Okay. So we could use a stir rod or a magnetic stir bar. Okay. I'll show you. It's literally a little bar that looks like a magnet that spins. I'll show you. All right, so now, you did a good job. Let me propose this to everyone. Number one, when you begin to boil your water, if you start out with exactly 1 liter of water and it begins to boil, what are the chances that you will end with exactly 1 liter of water? 0%, right? Because do you agree that some of it boiling is turning off? So, to get it back to 1 liter, is there a chance we may have to add some water? I love it. Even better. Add ice and let it melt. Okay? Now, my second question to you is, let's pretend... Yes, ma'am. Okay. My second question is, let's pretend hypothetically that the volume of water did not change when you boiled it. You put in 1 liter, you boiled it, and it stayed 1 liter. We've already discussed that's impossible, but let's pretend that it did. If that's the case, when you poured in that sugar, are we still at 1 liter? No. Does that make sense? All right. We're not going to go that deep. I'm getting you to think beyond normalcy. Okay. So, does the sugar take up space that water would take up? Yeah, so you did a good job, Nicole, but we need to adjust the way we approach this. And I think most of you would have said most of the things you said other than it was herbal tea. But here's how we want to adjust it. Now, this is not a very good description. We're going to deepen it, but this is the basics. So, this is where you will have to use words and sentences to explain. This could be a lab question on the free response. So the second thing that I need you guys to know is that word up there in yellow. So if you have a highlighter or you're circling things, circle that word in yellow. Standard solution. Okay? And what standard means is a known concentration. It is exactly known what the concentration is. Because did you control the moles of stuff you put in it? Did you control the volume of the stuff you're dissolving it in? So you know the moles and you know the volume precisely. We cool with that? Now, that's what a standard solution is. Now, we made sweet tea and we used a beaker. If I wanted to make a solution of barium nitrate, now we're kind of getting into the chemistry part. Is there really any major difference in making tea and barium nitrate solution? No, it's just a different solute, right? It's just a different solute. The thing that you're dissolving is different. It's still water. It's still all these chemical things, but you're just pouring something different in. Now, would we want to use a beaker to make a very, very precisely known volume solution? No. We have a tool that we use to make precise solutions. Anyone know what it is? Volumetric flask. So hold that thought. Paul? Yeah, I didn't mean to send it to you guys. All right, so here's the volumetric flask. What this is used for is to make precise solutions. Now, on the neck of that glassware, do you see something? It's a red line. Now, on the ones that we have, they're white lines. They're a little bit harder to see, but they're there, I promise. So let me ask you something. If we want to make, by the way, these glassware are precise for one volume and one volume only. You know, like graduated cylinders, you have different amounts. Beakers, you have different amounts. But that red line represents an exact volume. I'd be willing to bet that this is a 50, this is a 100, and that's probably a 250, just based on the comparison of size. But again, I could be totally wrong. So why would we want it to look like that versus it looking like this? Now, what is this? This is an Erlenmeyer flask. It's a different type of flask, okay? Or why would we not even want it to look like this? Why do we need it to look like that? Okay? All right, you're thinking of warming solutions. I'm talking about just a general volume. Nope. If I ask you guys to read exactly 100 milliliters, let's pretend that all those are 100. I know they're not, but let's pretend that they are. Is it easier to read 100 milliliters on that, or that? This one? Well, let me ask you something. What do you notice about the diameter of all of those openings? The diameter at that line versus the diameter of this one or that one. So, because the diameter is more narrow, is it easier to read a volume in this versus a beaker that's really wide open? Yes. This is why volumetric flasks are used. It's because the diameter is so small that you can easily read the meniscus. Does that make sense? So instead of us using beakers to measure out volumes, why do we use graduated cylinders? It's more precise. They're smaller. It's a lot easier for us to use this than it is for us to use something that's wide open like that. Even volumetric flask, do you agree? Even though it's more narrow, it's still wider where we need it to be. Where this, it's precise. It's exactly that amount. You fill the meniscus up to that line, you know exactly how much you have. Okay, very good. So that's the glassware we're going to use. Now, I kind of skipped a step, and I didn't mean to skip a step. But first of all, if we're doing barium nitrate, we need to know exactly how much we're putting out. But here's the problem. Can you take a digital balance and weigh out a certain number of moles? No, you can't. So if you know your number of moles, would you have to backtrack to find the grams? Yes. So we would need to do a conversion, figure out the grams, okay, and we would mass it out as accurately as possible. Does that make sense? Then we would pour that solid into a volumetric flask. Okay. Now let me ask you something. Why am I pouring it in before I put the water in? It dissolves, and does it take up space? Yes, we're going to go ahead and do that. Now, the next part, we're going to add distilled water. Why does the distilled water part make a difference? Okay, could potentially tap water make whatever it is react, potentially. Yes, and you don't want to unpurify. You want it to be exactly water and exactly barium and nitrate. That's all you want in there. Okay? To dissolve the solid. Go ahead. I don't follow your question. Yeah. Yeah, well, that's the same concept. Now, I want you to reread that again. It says, add enough distilled water to do what? Dissolve. Did it say fill it up? No. Why do we want to dissolve it first? Because once it dissolves, is it going to take up a different amount of space than it was when it was a solid? Yes, so we want to go ahead and get it dissolved so it can take up the space that it's going to take up the ions, and then what do? Then fill it up. Add enough water to the mark on the flask. So does this make sense? Now, this is really deep, but logically, does this give us a very precise solution? And when you're working with precise measurements, you need to make precise solutions. And this is how we would need to do it. So if you dump a solid into 1 liter of water, you are neglecting the space the solid will occupy, and your solution will not be correct. So if you do it, if you fill it up to 1 liter and then pour the sugar in, is it going to be exactly 1 liter? No, it's going to move up a little bit, right? So let's pour the solid in, put in some water, dissolve it, then fill it up. Does that make sense? Make sure you know this. I know that it's kind of deep, but it is what it is. Question, somebody. Okay? So this is another way to read it with a picture. Okay? They weighed and mounted a solute. Okay? First of all, if they gave it to you in moles, what would you have to do? Convert it to grams. Then they're going to put in enough water. Look at picture B. How much water did they put in here? And you can add this if you want to. Enough to dissolve the solid. Okay? Enough to dissolve the solid. I'm going to get very good, but I'm going to get there. So, okay. So, do you agree that this right here, it takes up a certain amount of space? If you poured it in there and you just filled it up, and then you begin to swirl, will it dissolve? So let's say that we did this and I poured all the water right up there. When you begin to stir it or swirl it, will it dissolve that solid? Yes. Does the dissolved solid take up a different amount of space than the solid? I know that's a weird way to say it. It may be above or it may be below. It depends upon how it breaks down. So let's go ahead with some room. Let's go ahead and get it dissolved. And then fill it up, right? Now, Justin's already made this notice, or made this observation. What happens to the color of that solution? Okay? It gets lighter. I want you to write this word down. Totally just went blank. No. It's absorbance and... Okay. Write those two words down, please. Absorbance and transmittance. Now, this is a complete and total off-topic tangent, but I want to throw something at you real quick. Remember those Velcro things? Here's a really big Velcro thing. Does concentration, first of all, before I even ask that, what the heck is absorbance? No. Yes, I understand your definition. All right, so let me back up even further because I'm doing a really bad job of this. All right, absorbance and transmittance. Now, I need you to add this because I'm going to write it up here because I ran out of space. That's going to make it a little bit more sense. We're talking about absorbance and transmittance of light. Are absorbance of light and transmittance of light two different things? Okay, what does absorbance of light mean? If I take a solution, yes, but not to the degree you're talking about. But yes, we're going to get there. Absorbance of light, if I take a solution, I shine a flashlight through it. Absorbance is the amount of light that stays in the solution, right? It does not go through. Okay? What is transmittance? How much comes through? Would you agree with that? So how would you calculate transmittance? It's the initial minus the final. What is absorbance? Final minus initial. Does that make sense? Absorbance, you want to know how much was absorbed. Do you know what it started with? Do you know how much it ended with? Final minus initial. That's how much was absorbed. Exactly. That's how much light was absorbed. It's taken away from the initial. Does that make sense? So, so let me ask my question again now. Does concentration affect absorbance and transmittance? Yes, that is my curveball. That is my tangent. I'm going to stop there. We will get to how does it affect and what can we do to calculate the absorbance and the transmittance. We're going to do a little mini lab on that. Now, real quick, just throwing it at you. what do you think concentration, and let's just focus on absorbance right now because they're opposite, right? Absorbance is opposite of transmission. What happens to the absorbance as the concentration goes up? It also goes up. Are you with me? And let's talk about why. And I really didn't want to get off into this. I'm such a bad teacher. So here's my deal. And I know this looks crazy. This is a terrible drawing. I've got two solutions. They're both exactly 1 liter. One of them is a half a mole. One of them is 1 mole. What is the concentration of the left beaker? Duh. What do brackets mean? Very good. What is this molar? Now, that little yellow box with stuff shooting out of it is a flashlight. All right. So here's the deal. Now, my question to you is, what does each little dot represent? The solute. The solute, right? So my question to you is, can compounds absorb light? Yes. Which one has more solute molecules in it to absorb the light? The one on the right. So the higher the concentration, the more or less absorbance. More. Now what does that tell you about the transmittance? So the higher the concentration, the less gets through it. And the reason why on the microscopic level is what? No. Keep going though. No. What is in the beaker that doesn't allow the light to go through? The solute. The solute is what is absorbing that light because chemical compounds can absorb the light. Now, I'm going to ask a question. My class last year, hold on, I want to make sure. How does light travel? What's it travel in? That's the speed, but what it travels in a form. Yeah, very good. Starts with a P. Photons. Yes, no? It travels in a photon? Okay. A photon, this is going to be crazy, so I need to spend the time saying this. A photon is a ball of light. Okay, and this is the crazy part. It's a ball of light like a paintball. Has no mass. It wasn't just you. Okay, so it has something called particle duality. Thank you, Dustin. And what that means is it travels like a wave and it travels like a particle. So, I need you to picture this. It's a paintball. A paintball. If I shot you with a paintball, how would you expect it to travel at you? Straight at you. But it doesn't travel in a straight line. It travels like a wave. Well, I'm talking about it like a wave. It has an amplitude, it has a wavelength, it has a frequency. Okay? So, light, as it's shot through this thing, those photons hit those molecules, and the molecules absorb the energy. Okay? Yes, sir. Yeah, I will. Schrodinger's cat, yes. All right, so let's read this at the bottom again. steps involve the preparation of a standard solution. A massed amount of substance, the solute, is put into the what? And this is important. Volumetric flask, and a small quantity of water is added. What's the purpose of the quantity of water? To dissolve the solid in the water by gently swirling the flask. Now, that's a new thing that we've added from the previous one. Does that add a little bit more depth to it? Okay? With the stopper in place. Now, yes, no, maybe, whatever. More water is added until the level of the solution reaches the mark etched on the neck of the flask. So do you agree it just kind of gets better and better? Are there some things that we could add to this? Let me see what the next slide says. That we could make it a little bit better. What are some things we could add to this to make it even more precise? No. Could we use a magnetic stir bar to swirl it? Sure. It is weird. But how do you get the bar out? And it takes up space. And it takes up space. Well, how do you get it out without getting water out? Or you could just get a magnet bar, like a wand that sticks down in there and pulls it out. All right, so let's just go on to do this real quick. You pour the solid in, you put a little bit of water, you swirl, right? Swirl, and then fill it up with water to what? To the line marked the etch on the glass. Does that make sense? Sometimes you do. Okay. Now, here's the way we could be more specific. You could state the compound being weighed. Could you say barium nitrate? Could you say sucrose? Could you say whatever the compound is? Okay. The exact mass of the compound. You could say it's 3.2 grams of barium nitrate. You could say it's 15 grams of sucrose. Do you agree that's very specific? Okay. You could state the size of the volumetric flask, and you're putting that in a 100, 200, 350 milliliter flask. You with me? Could you state that you're using hot distilled water or warm distilled water? Why would that be any more beneficial? What dissolves things faster, hot water, cold water? Hot water, okay? You may want to mention the word sterile or swir, and do me a favor. I have forgotten to take this off. These last two things right here. It says if the mass is less than 50 grams or the mass is more, completely cut that out. Ignore those two bullets altogether. We don't want to do that. Ignore it. Basically, what I need to replace that with is fill it up with enough water to dissolve. That's what that's referring to. Okay. Then state that you'll fill the volumetric flask the rest of the way. Now, I want you to add one more bullet, and we're done. After you add one more bullet, the very last thing you need to put is exactly what you made. The concentration and the name of the solution. And, the last thing needs to be the amount, the concentration, and the formula of the solution. So you could say that I made a 1 liter 0.5 molar solution of blah, blah, blah. Volume, concentration, and name of solution. That always needs to be the last thing, is tell me what it is. Molarity.